Hello, and welcome back to my YouTube channel. My name is Professor Gavala, and today I'm going to be talking to you about the Cascode Amplifier. And this is going to be the first part of a three-part series where we're going to be talking about the Cascode Amplifier. And essentially, we're going to talk about this circuit here to the left. We're going to talk about its small signal, and we're going to conclude and talk about the AV gain as depicted up here. So the first thing we want to talk about is why our Cascode amplifier is important. And we want to note that they're important because they have a high output resistance leading to a more ideal current source. And I'll draw a quick graph to show what I mean by an ideal current source. And additionally to why a Cascode amplifier is important is because due to this high output resistance, we get a higher gain than a normal amplifier. Consider something like the common source or the common source with source degeneration. In a previous video, we talked about the first point. And we said, consider that you have this common source with source degeneration. Let me call this M1. And let me call this current here ID. Right? So again, remember Vout is the same thing as VDS. And we said that, okay, if we drew a IV curve, so ID, and this is VDS. We said that the first part, as we increase VDS, until we reach this VTH, this is my cutoff. And then my triode is this, for a common source with source degeneration, it's this VGS or VN, okay, plus RSID minus VTH. Again, I talked about this in a previous video, so please make sure to check that out. And this is the saturation region here. And essentially, this lambda, we want to be extremely close to 0, where lambda is 1 over RO, where RO is just R out. So R out equals to RO. We want to be extremely high, very close to infinity. So the more or the higher R out is, the more this saturation region acts like an ideal current source, which is something that we desire. And the Cascode amplifier allows us to get an R out that is bigger than a regular common source amplifier. In addition to a more ideal current source that the Cascode brings, we get a higher gain. All right. So if AV for a regular amplifier is, let's just say, Gm Rout, for a Cascode, it's going to be Gm Rout times what's called a boosting factor. And we will show what this means as the video progresses. All right, coming back to this slide, we want to see how we get from here to here. And we need to note that whenever we're doing small signals, this is also called AC analysis. And we note that a DC voltage source is going to be shorted. So that's why here we have a short, or it just goes to ground. And a DC current source, ID, is going to be open circuit. So you can imagine here We have an open circuit, and this is grounded, which is why we don't draw it. And we note that M1, this MOSFET 1, can be depicted as a current source in parallel with a resistor. And M2 is the same thing down here. All right. And obviously Vin is an AC source, and we're doing AC analysis, so it remains. So I hope this conversion, or this small signal, and how we drew it out makes sense. If you have any questions, please leave it down in the comment section below, and I'll be sure to get back to you. Now, what I want to talk about is this equation. And I want to talk about how this equates to this. And I'll call this a side note. Okay, so we want to talk about the side note, which is basically another way to find voltage gain. And we say that, imagine you have the following: a voltage source. Let me call this a linear circuit, LC, and a Vout, where this is Vin. We can say that the transconductance Gm, is equals to an I out over a Vin, when Vout is equals to 0. So what we're going to do here is we're going to go ahead and short circuit this Vout. So this becomes a short circuit, so it goes away. We're going to then measure the current I out that is seen here, given that we have a V input. So that's our transconductance. And then, so let me call this step 1. And then step 2, consider the same situation where this is a linear circuit and you have a Vout and this is Vin, and you're tasked with finding R out. So R out in this situation is the same as R Thevenin, which I've talked about in previous videos. And if you did circuit analysis 1, you should know about R Thevenin. So this is equals to your voltage output, Vout, over your voltage output, Vout. Sorry, your current output, I out, when Vin is equals to 0. So essentially what happens here is I'm going to attach a Vout, and I'm going to see the I out coming in. And what I'm going to do is I'm going to short circuit this Vin. All right. And the idea here is AV, which is equals to Gm Rout, is equals to I out over Vin times Vout over I out. So then now my I outs cancel out, and I am left with Vout over Vin. And in most circuitry, you could use this equation. You could find your Gm and your R out to get your voltage gain, or your transconductance and your R out to find your voltage gain. And what we say is this approach is sometimes easier than finding an equation for Vout in terms of Vin and solving for Vout over Vin. For the purposes of the schematic that we're doing, of the circuit we're doing, there's what you call an inversion property. So if you give me a positive Vin, I'm going to give you a negative Vout, right? If you give me a negative Vin, I'm going to give you a positive Vout. As a result of that, we attach a negative here, all right? So there's going to be a negative Gm Rout because of the inversion property. Okay, so now we understand this. If you have any questions, please ask them down in the comment section below, and I'll be sure to answer them for you. Okay, Now let's actually do the analysis. So we know that AV is equals to minus Gm Rout. So let's go ahead and find Gm. So we say Gm is this I out over V in when V out is equated to 0. So what I'm going to do is I'm going to go ahead and short circuit V out. Okay. I'm going to notice that this VGS goes to 0. As a result, this current source, this voltage controlled current source, goes also to 0. Then I am going to redraw my circuit with the idea that VGS2 is essentially V in. So this here is also, this term here is also V in. So let me redraw my circuit as this is a ground, this is RO1, and then I have this controlled voltage controlled current source. So this is RO2, and this is Gm V in. Okay. Let me go ahead and apply a current source I out. And this current source is essentially going to split here into IO2 and this current source. So I can write an equation and I can say I out is equals to Gm V in plus IO2. Now, in general, this RO2 is extremely big. It's extremely big, or you could design it to be very big. And as a result of that, most of your current is going to flow through here and not through here. So we can approximate I out to be approximately Gm V in. As a result, Gm is essentially I out over V in, which is equals to capital Gm. So approximately speaking, your transconductance, big transconductance Gm, is equals to Gm, in this case, Gm2. Right? Okay. So that's the equation for Gm. If you have any questions, please ask them down in the comment section below, and I'll be sure to get back to you. Okay, the next section we need to solve for, again, remember AV is this Gm Rout. We need to solve for Rout. All right. And we've done this in a previous video. Again, check out the common source with source degeneration video. So we've done this in the previous video, but I'll go ahead and walk through it again. And we note that Rout, the equation, it says Rout is equals to V out over I out. I out when V in is equals to 0. So what I'm going to do here is I'm going to get rid of V in. I'm going to send it to ground. I'm going to just attach a plus minus V out, and this pushes an I out here. So what could we say? We could say that VGS basically is equals to 0. As a result, this is also this voltage controlled current source is also equals to 0. And we could rewrite this as, or redraw this rather, as a VGS1, a GM1, VGS1, an RO1, an I out, and a V out. And we just have this RO2 going to ground. Okay, so let's go ahead now and write different equations to see what we can obtain. So what I'm going to do is I'm going to start here, and I'm going to write a KVL because I'm solving for voltages. And actually, before I do that, I'll say that, again, this is IO2, and this is, again, I out, because it splits on this node and comes back to this node. So I hope that makes sense. So let me go back to my KVL. Let me call this 1. And let me write a KVL for loop 1 and say plus VGS plus RO2 I out must equal to 0. So that means VGS is equals to minus RO2 I out. Let me call this equation 1. So let me write a KCL at this node. Let me call this node 2. So I can say then that I out is simply equals to GM1 VGS1 plus IO2. Again, this is 1 and this is 1. So then this becomes I out is GM1. I'm going to substitute this for VGS1. This becomes negative RO2 times I out plus IO2. Let me go ahead and solve for IO2, okay, by moving this term to the left-hand side. So IO2 is simply I out plus GM1 RO2 I out. Let me call this equation. Let me call this equation 2. All right. And then last but not least, I'm going to do a KCL right here. Let me call this loop 3. So minus V out is equals to, so this is plus minus, minus V out plus RO1 IO2 plus RO2 times I out. Then we go ahead and replace IO2 here over here. So we get minus V out plus RO1. I'm going to go ahead and distribute this as well. So this is I out plus RO1 GM1 RO2 I out. And then plus RO2 times I out. And obviously this is all equals to 0. I forgot to put equals to 0 here. So let me go ahead and move this to the left-hand side. So we get V out. And then I'm going to go ahead and just divide the I out. This equals to RO1 plus RO1 GM1 RO2 plus RO2. All right. And essentially, this is basically my R out that we wanted to find. But the nicest way to write this is R out is equals to 1 plus GM1 RO1 RO2 plus RO1. So essentially, right, we're considering the transconductance of my first MOSFET, okay, times the resistance in parallel with it times this resistance plus back again the RO1. So this is an equation you want to memorize as well. It's really good when it comes to analyzing these circuits pretty quickly. Okay, so now we found everything, right? We found our GM, so we know AV. We can say here that AV is minus GM R out, which we know this is minus GM, we said GM2 times 1 plus GM1 RO1 RO2 plus RO1. Okay, so we can say then that this is minus GM1 RO1 times GM2 RO2. And this was the boosting factor I mentioned earlier in the video. that the Cascode Amplifier brings. And again, you can solve this circuit by doing Vout over Vin, but it will be a little bit harder, and it might be a lot more steps than simply just finding the Gm and the R out. Okay, so this concludes basically finding the AV gain of the Cascode amplifier. For the next part, so part 2, I'm going to be solving the Cascode amplifier with a resistance RD okay. And for part 3, I'm going to do the same thing, but with PMOSes as my current source, in place of my current source. So these are all biased, V biased. And V biased just means a DC voltage source. All right. So please look out for those 2 parts coming up. If you like the video, please like it, share it, and leave any comments in the section, in the comment section if you have any questions. Please like my videos and share my YouTube channel for me to grow the channel. And thank you.